Hey everybody. In this lesson, we're going to be looking at the difference of, or the difference of, the difference of two proportions. I don't know what I meant there. So we're going to be looking at two things. We're going to be looking at the confidence intervals, like how we construct a confidence interval for the difference of two proportions, as well as setting up and carrying out a test of significance on those differences. So let's look at an example. So let's say that a rare disease is killing many trees in our state. And we want to see if there's a difference in the number of trees that are being affected at a high elevation as compared to, say, a low elevation. So what we're going to do is we're going to calculate and interpret a 90% confidence interval for the difference in these proportions of all the trees that have died at those elevations. So just like with any confidence interval or significance test, we always check our conditions. So it's still the same three conditions. We check for randomness, we check for independence, and then we also check for normality. The only difference here, no pun intended again, is that we have to make sure that we do it for both groups. Like, was the data obtained randomly for the high elevation and the low elevation? Do we have independence for both elevations? And do we have a normal distribution for both elevations? So same conditions as before, you're just kind of doubling it, you're doing it twice. So let's have a look here. We know that we have a random sample of trees from both elevations selected, so that's good. We can assume that there's going to be more than 2,400 trees in the large forest for the high elevation, and we know that 200 is going to be less than 10% of all the trees in a large forest for the other elevation. For the third condition, where we're checking for large counts, i.e. normality, we basically check it for each group, and we have to make sure that we do the sample size multiplied by the sample proportion and the sample size multiplied by 1 minus that sample proportion. And as long as they're both going to be greater than or equal to 10, we're good. But remember, you're doing it for both sets of data. So if we look at this data, the conditions are all met. So we're ready to try and carry out and construct our confidence interval. So a confidence interval, remember, is two parts. It's the point estimate plus whatever the margin of error is. So the margin of error, basically means we're not going to be 100% accurate here. There's always going to be some error. The margin of error takes that into account, but it gets split up into two parts. Remember, the first part is the standard error of the statistic, which is our standard deviation. And the other part is the critical value, which is how confident we want our estimate to be. So the formulas that we're going to use for the standard error is this guy right here. Now remember, we don't know the population proportions, so therefore we have to use p hat 1 and p hat 2 as an estimate. And also because we're combining the two distributions, we have to follow rules for that. So we get this formula right here. So this is really just the combination of the two different standard deviations. You'll find this formula on your formula sheet if you ever forget it. So let's go ahead and plug in our information. So let's figure out our point estimate first. So right here, for the high elevation, we had about 15% of the trees getting the disease. And in the lower elevation, we had about 12.5%. So that gives me a point estimate of about 0.025. So it's kind of close to zero. It seems like there's a little bit, maybe there is a difference, but definitely close to there being no difference. But remember, here we're trying to figure out a confidence interval. So for 90% confidence, remember we use z-scores for this. So our critical value is going to be 1.645. And then similarly, we have our standard error right here, which is basically a combination of the two different standard deviations. So you put all that together, and here we have our confidence interval. So we're going from negative 0.029 to 0.079. Now you can also do this on the calculator, which I'll show you on the right-hand side here. So we're going to go to Stat, we're then going to go across to Tests, and then we're going to scroll down until we see our two proportion interval. In this case, it's our two proportion z interval. So we're going to select that. So now we're basically after all the information. So let's look at the first group. So we had 36 trees that caught the disease out of a sample of 240. And then for the second group at the low elevation, we had 25 trees out of 200. And then the confidence interval, we wanted it to be 0.90, so 90%. And then we're going to go ahead and calculate. As you can see, it's much easier to use the calculator, and we come up with the same exact value. So now we need to interpret it. So basically, if we are 90% confident that the interval from negative 0.029 to 0.079 captures the true difference, remember the high elevation minus the low elevation, in the proportion of all trees in the forests that have died from the disease. Now, one thing to notice here, the value of 0 is included in this interval. What that indicates is that there really isn't a difference between the two groups, because 0 would represent no difference. So in this case, there doesn't seem to be a difference between high elevation and low elevation. All right, let's go ahead and have a look at how we construct a significance test for the differences in two proportions. So we're going to use a slightly different example here. So this time we're going to look at pink eye. I know, a lot of you are thinking, that was the worst time. So the question then becomes, can eye drops containing azithromycin, hope I pronounced that right, can they make the recovery faster? So in one clinical trial, eye drops containing azithromycin were compared to a placebo eye drop among 279 patients suffering from pink eye. The results, well, of the 130 patients who were randomly assigned those drops, 82 were cured. And of the 149 who were given the placebo, 74 were cured. So this time, do these results give convincing evidence that azithromycin is more effective at curing pink eye than a placebo for subjects like the ones in this study? Okay, so the first thing we want to do is we want to set up our hypotheses. So we have our null right here, and we have our alternative one right here. So remember, you can write it both ways. So you can either say that for the null, for example, that P1 is going to be equal to P2, or you can specify it like this, where P1 minus P2 is equal to 0. You have to know how to write both ways and interpret both ways. Now, because we're trying to see if azithromycin makes the recovery faster, we're going to see if one's proportion is greater than the other one. And then don't forget, we need to also indicate what P1 and P2 both represent. So just like before, we always check our conditions. Let me just widen this a little bit here. Okay, so before checking those conditions, we do need to do something which is quite particular to a significance test for the difference of proportions. This is the only time you do it. And what you do is you pool the results, you combine the results. So for this example, the null hypothesis is the treatments that, they're going to be equally effective. So if that's true, then the best estimate of their effectiveness is to combine all the patients from both groups. So again, let me be clear. You always, always, always do this for when you're doing the differences or testing the differences between two proportions. Not for the confidence interval, not for any means, just for this specific test. So let me show you how to do that. So for the azithromycin group, we had 82 cured out of 130. The placebo was 74 out of 149. So when we talk about combining the proportions, we basically combine the number of successes and then combine the number of observations and then divide, and we get this combined proportion of 0.559. Okay, so now we're ready to carry out our test. So again, just like before, we're always going to check our conditions: random, independence, and also large counts for a normal distribution. So obviously the random here, we randomly, you in this particular case, we're randomly allocating our two different test groups to each of the different groups. That sounds stupid, but you know what I mean. We have two groups that the subjects were randomly assigned to. We also might want to check that when we're sampling without replacement, that the sample size is less than or equal to 10%. And again, you want to do that for both samples. However, in this case, because we're doing an actual experiment, you don't need to do the 10% condition. But if it wasn't an experiment, like if it was something like the tree example, then you would still need to do the 10%. The one thing that changes is when you assess normality. So instead of using P1 and P2 now, you're going to use the combined pooled proportion, but you still have to compare it to the sample size of the first group and the sample size of the second group and still make sure that everything is greater than or equal to 10. So if we go ahead and do that, we can see that that is absolutely fine. In each of these cases, the proportions multiplied, the pool proportion multiplied by the sample sizes is greater than or equal to 10. And like I said before, we randomly assigned the patients to the two different groups. And because it's an experiment, we don't need to conduct a 10% independence test here. We would if we weren't doing an experiment. All right, so let's look at our test statistic. I'm sorry, So to set that up, we know that the difference between the two proportions is going to be 0.134. All right, so just subtracting those two. And it looks like, there is a difference, but we want to see if there's a significant difference. So remember, the standardized test statistic is always the statistic minus the parameter divided by the standard error. So let's see what that looks like. So it's one of the larger formulas. So it kind of looks like this. I'll give you a moment to kind of soak all that in. Essentially on the top here, you have the difference in the two proportions. And on the bottom here, you have the difference in the two standard deviations, or rather the addition of them, but you're using the pooled value instead. All right, so once we do all that, and you use your normal tables, you get a z-value of 2.25, and you'll eventually get a p-value of 0.0122. Now, no significance level was stated for this test, so we're going to use a 5%. So because the p-value is greater than 5%, we will reject the null. Now, let me just show you how to do this on the calculator, okay? Because the calculator does it very fast. So we're going to stat, go across to tests. So the one we're looking for is the two proportion z-test. Click on that. So let's look, let's go back here and make sure that we've got our values. So x1, that was my first group. So 82 out of 130. I think that was the azithromycin group. And the second group, the placebo, it was 74 out of 149. And remember, we're trying to see if the first group is greater than the second group. Go ahead to calculate. And there's our information. There's our results. So as you can see, we're getting a p-value of 0.0122 if we round it. So there basically is convincing statistical evidence that one method seems to work better than the other. One thing to note here, though, is we chose a 5% level of significance, which means that we ended up rejecting our null. Had we chosen a 1% level of significance, we would have failed to reject our null. So that's when the type 1 and the type 2 errors come into play. So by adjusting the level of significance can give you a different conclusion. Anyway, get the practice at this. That's all the testing that we're going to do, with the exception of categorical testing a little bit later on. But the hardest part is going to be recognizing which test to do and to do it when. So for right now, just practice finding the confidence intervals and also testing for differences of proportions. If you have any questions, please reach out to me. Take care, everybody. Thank you for being so patient. All right, take care, and I'll talk to you later. Bye-bye.